All right, everyone, welcome back to the workshop. Our next panelist is going to be Gary Mallard, who's going to be talking through how to deal with co-elution. All yours, Gary.
Okay, thank you. I was assigned this question of how to look at co-elution, and I decided that one of the things we ought to start with is a definition of what we mean by co-elution, because to a certain extent, that definition is a little bit different for different people. And so this is my start on that process. It is, what is co-elution? And fundamentally, it's that the chromatic baseline is not attained for one component before the next one begins eluting. So typically that looks, or one of the many ways it looks, is something like this. You've got what looks like the peak, starts back down, and before it gets all the way back to the baseline, it starts back up again. Now, at one level, I would have to say that these are not very hard problems to solve. And the reason I say that is because if I want to understand what these two components are, in general, I can sample that. I can take a mass spectrum at this point, and I can take a mass spectrum at this point. And what I get is, in many, if not most cases, extremely good identification. So in that case that I just showed you, this is the earlier component scan, and this is just a single scan. This is scan 1239. This is scan 1247 in that data file. And I get extremely good identification. You'll see that I've got an identification factor of 956. I have a lower probability. That just simply means there's other components in there in the library that have very similar spectrum, and a match factor of 947 and comparable fairly high quality, but not great probability of correct identification. So, but the other thing that you might often want to know in a situation like this is not just the identification, but you may actually need to quantitate the data. You may need to say, well, how much of something is there? Because there may be a threshold for whether or not it's considered illegal, or just generally you want that information. And for these kinds of data, you're still in pretty good shape. So for this, I'm using, in order to do concentration measurements, I'm using selected ion data. And in this particular case, I'm using the base peak, which isn't necessarily always what you want to do. But this is the base peak of those two spectra. And you see that there's almost no interference in the base peak. So when we have separations like this, that is to say that we actually have a real minimum in the TIC, there's a good chance that we're going to get really no fundamental problems with the data, with understanding what the components are and getting the areas for them. Now, there is one caveat for this, and that is that if these two spectra are extremely similar, then you can begin to have problems. But this isn't the only thing that we could say represents co-elution. Let's ask what happens if there's even more overlap. And to do that, I'm going to bring up a data file that happens to be a group of pesticides, and when you look at this data, this is a fairly small fraction of a much longer chromatogram. And when you look at this data, it looks like we have some cases where there's something that looks like what I was talking about before as a co-elution here and here. And then you look here and say, well, maybe there's something going on there. I'm not really sure. Maybe that's got some bad chromatography there. But I want to examine closely two of these peaks. I'm going to start by examining this one, and then we're going to examine this one. So we're going to examine this peak, and I'm doing all of this within AMDIS, and so this is just a take it to the screen and blow it up. And when I do it, I get this. And once again, it looks like at first glance that I've got a fairly clean TIC. And it's at the point that you go beyond the TIC and look at the individual ion chromatograms that you begin to see that there's something quite different going on there. And when you look at the individual ion chromatograms, and I've pulled 3 of them up here, you see that there's a 201 that peaks very early. There's a 252 that's peaking, it's larger and peaking a little bit later. And there's a 248 that's peaking a little bit later. So within this manifold that looks at first glance like a single peak, there are in fact 3 distinct components. And we know they're distinct because the ions are rising and falling at different times. And as Ed discussed in the previous talk, the way AMDIS works is that it looks for these ions that are rising and falling, and it says what other ions are rising and falling at the same time. It finds the ions that peak at this time, and it associates them. It finds the ions that peak at this time and associates them. It finds the ions that peak at this time and associates them, and then looks to see if the shapes are right. And from that, it generates a spectrum. Now, what I showed you in the previous example was a case where if you simply took a spectrum at one peak and a spectrum at another peak, and those peaks were in the TIC, not in the selected ion chromatograms, you would have gotten pretty good matches. But you can see here that you're going to have very significant interference in here. If you were to take a single scan at this point, you would have significant contributions from 3 different components. Now, it's quite possible sometimes to actually separate those out and pull them apart, but it is by no means guaranteed. And what AMDIS does for you is it basically does a deconvolution. It looks at the shapes of these things and pulls them out, not based on the spectra in a library, but based on the shapes. And I noticed one of the questions that came up in the discussion of Ed's talk was whether or not you needed a library to do the deconvolution. And the answer is no. You can do the deconvolution. That is to say, you can find all of the components in the data file without having a library at all. You don't identify them. You have to do something else. But what you get out of it are pure spectra. And those pure spectra can then be sent to the NIST library, or they can be handled within AMDIS itself if you have a target library built into AMDIS. And I'll discuss that just briefly later. So this is much more close to what I would call a true coevolution. That's to say that there is no point at which the TIC, this white line, ever dips down during this entire profile. And so there are 3 components here, and we can, and AMDIS has, successfully identified each one of the 3 components. So what appeared to be a single peak is actually 3 different things. And there is, as I said before, no place in this where if you just go and take a single scan and search it with the library, that you would get really clear, unambiguous data. So given that, the other thing I want to point out is that in addition to identifying that there's separate compounds, AMDIS also tells you exactly what the area of the TIC would be if that was the only compound present. So for this component, this would be the TIC if only it was present. For this component, this would be the TIC if only it was present. And for this component, this would be the TIC. Now, the question, so you not only can get identification, but you can get areas. And it's useful to say, well, how good a job are we doing? And so I just want to show you what happens when you take these three components here, the TICs, and you sum them. Oh, that's right. These are the three components that we found. And the data, both in terms of the RI values and the spectra, agree very well. But the real question that I want to explore a little bit more is, are we actually also getting quantitative information out of this? And here is, unfortunately, you can't do this with an AMDIS, but you can take it out into a spreadsheet and do it. And here are the TICs for the three components. They're the blue, the orange, and the yellow with the triangles. This is the experimental TIC that you get from the instrument. And so if I add the three TICs, the proposed TICs that AMDIS has created, as if there was nothing else there, what I get is this little purple line. And you can see how well that TIC for all three of these compounds compares to the experimental one. The worst case is there's about a 5% difference between these two. So what I'm saying to you is that AMDIS, at least in this situation, is capable of identifying these compounds, and even if it didn't have the material in the library, it would identify that there are three distinct components there, so that you would recognize that you weren't dealing with a single pure peak. And it also gives you accurate areas, so that if you need concentrations, you can use those. You can get that information out as well. Now, I'm going to go back to that chromatogram that I showed you, and I'm going to look at the next peak and again examine some of the things that happen within the data file when we start looking at what looks to be a little bit more complex data. And when I blow this one up and look at some selected ion chromatograms, what I'm seeing are, I've got two ions here, 79 and 238, and here's the raw data. I'm taking the raw data at this point. So you see that I'm looking at this 79 ion, and I'm looking at this 238 ion. And I'm looking at them as much as anything. We'll see that they're different, but they're also of comparable size, and it's a lot easier to see what's going on. And what you see here is that one of these ions appear to peak on successive scans. But in reality, and this is one of the things that AMDIS does, AMDIS fits these ions to within a tenth of a scan. And so the real place that these two ions peak is about half a scan apart. And this shows you where these ions actually peak, at this point and in this point. So we're looking at two things that are very, very close together. And the question is, can we resolve? I mean, we are being told that they are different by AMDIS. And the question is, now, can we identify them? And the answer is obviously yes, although I'm going to show you a case later where the answer is a little bit more ambiguous. And even though these things are only about half a scan apart, we're going to see what AMDIS can do with them. And we have the two components here, and now we have the spectrum of each of the components. Now I'm showing you not the raw spectrum, which would mean that this little click down here was red, but I'm showing you the extracted spectrum that AMDIS gives. And on the next slide, I'm showing you the extracted spectrum from the other one. Here's this further, here's the nearer. You might look at that and say, wait a minute, those are exactly the same thing. What is he telling me? They're different? They're really the same. And what the difference is a little hard to see here, and I'm going to blow it up so that you can see it. But the difference is that some of these peaks are uncertain, and I'll explain what that means. So I'm going to go to this one, and I'm going to blow up this region right in here, right around 137, so that you can see it a little bit better. It's hard. It's easier to see this when you're working with AMDIS as a program, and it's a little hard once you've got these view graphs up. But what you see here is a dashed line. Now, what that means is that AMDIS isn't really sure that that ion belongs to the component it's extracting. It's an uncertain peak, and you notice that the 181 is an uncertain peak. But the 149, it says, it is definite. That's really there, and it's not so obvious, but down here the 79 is too. So, you have the option, by the way, and I'll show you in a minute how that looks. You have the option of just not showing the uncertain peaks at all. So this is sort of the default. The uncertain peaks are dashed, which at times can be hard to tell. But basically what this is telling you is that there are ions here that are hard to sort out. And there's a set of algorithmic criteria, and depending on how you set those algorithmic criteria, sometimes things can be uncertain and not uncertain. Sometimes they'll go all the way to not being certain, but there are disadvantages to this. What I'm using here is the default out of the box. This is how AMDIS comes if you just download it, start running it. This is what it looks like. You may at times want to change that, but we're not going to discuss that today. So but I'm going to use this region of the chromatogram to illustrate a second tool that we've got for dealing with co-elution. And that tool is buried not inside AMDIS, but inside the NIST database program itself. So I'm going to take the raw data, which is indicated by the fact that I've got this little red arrow here, and this is just the raw scan data. And I'm going to send it over to the NIST program. And this is what I get from that. I get a hit. I get a hit with a pretty good match factor, 822. A pretty good probability of correct identification, which is 884. And I look at this thing and I say, well, that spectrum doesn't look bad until I look at it a little bit more closely. And what I discover when I look at it more closely are two things. One is that there's a cluster of ions, and admittedly they're low-mass ions, and one is always more suspicious of low-mass ions. They're low-mass ions, but there's a cluster here that aren't matched at all. And there's also a slightly higher mass, 149, that is very poorly matched. So whenever you see something like that, you at least have the suspicion that maybe what you've got are two components that are overlapping. Now, AMDIS has already told us that. Okay, so in some respects, there's a little bit of duplicity going on here. But AMDIS has told us up here, in putting these two triangles up here, that there's two components there. So it's not surprising that we find this, but the question is, what is it? Well, if it's in our AMDIS library, if it's in the library we use for the target analysis at first, we may already know what it is. But it's often the case that it's not. And what you want to be able to do is use a larger library, including your own library, a library that you build yourself from standards that you have acquired or material that you have seized in various ways. And the way to do this, particularly in a situation like this, is to use the tool that's hinted at here, this little button here, this little tab down here called subtraction. And that does a spectral subtraction. It basically takes the unknown, which is here in red, and subtracts the spectrum in blue that's the hit. and it's not necessarily the hit, it's just whatever you're putting in that screen, whatever's in there, it makes a subtraction of that. And it generates a new spectrum. And once you've got that new spectrum, you can search it. It's no different than any other spectrum. You can just simply search it within this library. And when you do that, here's that subtraction spectrum, and you see it says it's a subtraction of this scan minus this compound, the spectrum for this compound. So that's the spectrum that we're now searching. This is the comparison between the search spectrum and the library spectrum, and it's a very good match, 823, and a probability of 89% that it's right, and it matches CAPTAN. So, so what we have done here, and I'm going to go over this in real time. I'm going to actually do this for you on the screen. But what we have done here is basically gone through the process of having something that we didn't get a very good match for. We were suspicious that there might be a second component there. And we were particularly suspicious because AMDIS has told us there's a second component there. And then we've used the NIST search software to give us at least a beginning idea, and we'll see probably a good identification of this particular component. And I'd like to just go through that process, not with slides here, but in real time with the mass spec database. And so let me go over to AMDIS. And so this is that. This is a piece of that chromatogram that I showed you before. And if you'll remember, the very first thing we looked at is this little section in here that had these three components in it, that one, and then that one, and then that one. And then now we're focusing on this one over here. And as I said before, we can either look at the individual components. And when I look at the individual components, I see that I've got, I'm going to blow this up so you can see it. It's a little hard to see that this is dashed. It's even harder to see it here than it was before, I think. But that's okay, because I can tell it not to show the uncertain peaks. And when I do that, it only shows me the peaks that it's confident of. So for this component, these are the confident peaks. For this component, these are the confident peaks. And as you can see, 79 is, if I tell it to show the uncertain peaks, you see the 79 is uncertain. And you can see why, because it's not peaking much different than the other peaks. And if you were to do this in a conventional way, where you average this entire thing, you really wouldn't get rid of this 79. But I can not show the uncertain peaks. And then it becomes very clear what I've got here. I've got this set of peaks, and I've got this set of peaks. But what I want to demonstrate here is how to use and I could search each of these, and maybe I'll come back and do that. I could search each of these with the mass spec database. I could actually make use not of the identified spectra, but of the spectra that have been deconvolved. But what I want to demonstrate here is this whole idea of doing a spectral subtraction within the framework of the NIST database. And so I'm going to do a search with this spectrum, which is the raw data. You'll notice I got that by clicking down here. I'm just looking at a single scan, and I'm going to go to the NIST library, and I'm going to search it. And what I got was exactly what I'd already shown you. And here is what it looks like head to tail. So here is the unknown, which is just that single scan. Here is the best match, And you can again see that there's peaks that aren't matched at all, and there's peaks that are matched very poorly. And so the question really is, what's the next step? And I've already discussed the next step, but I wanted to show it to you in real time. And that is that I simply go to subtraction here. And once I've gone to subtraction, what I see is the difference between this raw data and this subtracted data. That's what gets me the subtraction. And then to search this, I just right click and I say do a library search on this. And now I've got an identification of captan. So I have basically, and I'm really just repeating what I've already showed you before, but I'm just doing it in real time. And showing you how it's done. I've basically been able to subtract captan, to subtract the first hit, and I get captan out of that. Now, one thing I would like to do is I would like to go back, and I'll go back to my original scan, and I'd like to subtract captan from this and then research that. Well, if I look down this list, I don't see captan anyplace, right? So I can't readily do that. So I just to illustrate how to do that, I'm going to go over here to and I'm going to search in names for captan, CAPTAN, and now I've got a spectrum for captan. I'm going to send that spectrum to the compare list. And what's already in the compare list, because it's the last thing I searched, is the history, and it's that single scan. And so now here's the head to tail. This is captan and the single scan. And I can again, just by clicking on this button, I get the subtraction. And I can search that. And now, of course, this is not a surprise. I get exactly the same first hit. But the difference is my first hit now has got a 905 match factor and a 93% chance of being correct, whereas what I had before was an 822 match factor and an 84% probability of being correct. So I have, in effect, gotten a better match for my data. And I did that simply by doing the subtraction of the minor component that I had found by doing the subtraction of the major component from the raw data. So I think of this as closing the loop. That is to say, I have basically taken one data point out, one spectrum out of that mix, and I said, okay, I'm taking that thing out, and then what's left, and then I'm taking what's left out, or what showed up once I took that out, and take that out. And I've gotten, in both cases, I've gotten substantial. I've gotten, from having no identification of captan, I've gotten a good identification. I've got something in the high 800 regions. And I've gone from having a pretty good identification for the other pesticide to having a very good identification for that other pesticide. So we've got here a tool that we can add to AMDIS for those really difficult problems. And the problem that we attacked here was not one that AMDIS actually hadn't been able to solve. It was one that AMDIS had solved. And I'll go back to AMDIS, and if I look at these two things, I'll bring the answers over here. You see that it's actually already identified these things, but that's because they were in the library. If they hadn't been in the library, there would just be little triangles here, and I would have been able to search them with the NIST program. So let me go back to my PowerPoint presentation. That was my demonstration. And and just to remind you, AMDIS did find these two things, but I thought it was useful to go into them and say, wait a minute, there's something more that I can do here, and the thing that's more that I can do here is to show you how to do that subtraction. Now, the reason that I wanted to emphasize that is because there are some limits to what AMDIS can do, and this is an interesting case of those limits, and it's where I want to show you the use of the subtraction. So this really does appear to be a single chromatographic component, both visually and in terms of what AMDIS is showing. AMDIS is showing some other little things here, but they're all very little tiny things that are mostly noise. They just represent. But this is the scan that really represents essentially all of this data, except a little background. And when I send that to the NIST database, what I get, and this, by the way, in reference to something that Ed said earlier, I'm actually not using the current NIST database to do this search because it doesn't happen to have the compound I need in it. But this is a series of new compounds that we've added to it, and there's something like, as I think Ed mentioned, there's something like 200 and something. These are fentanyls, and there's something like 200 and something fentanyls being added. So when I do this search, what I get is a so-so identification. 792 is not a particularly good identification. 778 for the next hit, 766, 740. I'm just showing you the top 4 hits. But one of the things, and the probabilities are correspondingly not very good. And one of the things that you did, just notice carefully that the first 3 are all isomers of one another. That is to say, they're all the fentanyl base with either a cyclopropyl or a propionyl or a crotonal end to it. And then the next one is something different. It's no longer in that same class. But these 3 are all isomers, and so it's maybe not surprising that those 3 compounds all have similar spectra. And when you look at them, you see that they do. If I look at the second one, you see, and if I look at the third one, you see. And in all cases, you see 2 things that are very prominent. One is that none of them explain this very large high mass peak at 261. And none of them explain this peak at 218. And none of them really have 158s that are very good. If I go to so that's really all 3 of these spectra are missing major high mass peaks, which is why, in effect, they have match factors below 800. You simply won't have a good match factor when you're missing a major high mass peak. You can miss low mass peaks and still get good match factors, but you can't miss a high mass peak. And the reason you can't is because high mass peaks are far, far more important for the identification of a compound than low mass peaks. And the algorithms that are used within NIST and within AMDIS emphasize the higher mass peaks more than the lower mass peaks. But when I go to the 4th one of these, I suddenly see a very different pattern. Now, notice that in all of these, maybe you didn't notice, but let me just remind you that in all of these, most of this region here, up to about 158 or so, was pretty common. It basically got it all well. The problems were with the higher peaks. And in particular, we were missing this 261 and the 218, and the 158 had fairly poor matches. But now suddenly we've got the reverse situation. We don't get the 257 in this thing. We get a really good 218, and we get a good 158. So this almost immediately would imply, if you go back to these things, it would imply that you've got a mixture here. You've got a mixture of the thing that has the 257, or maybe more than one thing, but definitely one thing that has the 257, and the thing that has the 261. So very much the way I did before in the other case, but here, if you'll remember, AMDIS did not find two components. We find two components in this particular case, or at least I shouldn't say we find two components. We suspect two components because of the results from the mass spectra alone. That is to say, the mass spectra alone is telling us there's something funny going on here, that we're missing in three of these cases. We're missing the highest mass, highest large mass, the highest intense mass peak, and in one of the cases we're missing the next highest. And so the suspicion is that there's some sort of a mixture being analyzed here that's not being separated by the chromatography. And so to do that, we say, well, let's start. In this case, we're going to start in the reverse direction. We're going to start by subtracting the fourth peak. That is to say, we're going to subtract the thing that has the 261. Remember that the 261 is present in the methoxyacetylfentanyl. So I'm going to subtract it, and then this is the spectrum that I get from that subtraction. This is the spectrum. I'm pointing with this with my finger, and you can't see that, can you? This is the spectrum that you get from that subtraction. So the spectrum for this molecule was subtracted from the raw data. Right? This is the raw data. This is being subtracted from it. You can see that it's going to take out the 261 and leave the 257. And once again, I can search this spectrum. And when I search this spectrum, I get again the cyclopropylfentanyl, but we get it with a much higher match factor. And we still get the crotonal fentanyl and this other fentanyl, and we get the fourth isomer. So these are all of the four possible isomers of this fentanyl with this C3 attachment to it. There are no other possibilities. And so we've basically exhausted these things. And what we have found in doing that is that we still have a problem in that this match factor is high and this match factor is high. And so, and this match factor is high. So what we know is it's one of these three. We really don't know which one. So we haven't resolved it. And that's often the case. Sometimes you just simply can't resolve it. We will look at least slightly reducing the scope of this. But now let's go one step further. And now let's subtract the cyclopropylfentanyl, the best match. And this is what I've already just said, that the cyclopropylfentanyl has increased its match factor from 792 to 880 when going from a single scan to the subtracted search. So that's a nice improvement. It's a nice improvement in quality. And when you look at this spectrum, you don't suddenly say, wait a minute, there's something wrong here. There's just something missing. You know, I'm not getting that 261 because the 261 was something else. We can go and do the other thing, though, and that is to say that we can subtract the cyclopropylfentanyl from everything, and then we can search that, and lo and behold, and this is probably no surprise, we get the methoxyacetylfentanyl. Now, once again, from my point of view, we've closed this loop. That is to say, we've taken a complex spectrum, we have searched it, we've taken what looked like the best hit, and we have subtracted that, and then we've searched that again, and then we have taken the thing that resulted from that, and in this case, which happened to be the the methoxyacetylfentanyl, and we've subtracted that from the data and searched it, and we've basically closed the loop, and we've said that it's reasonable to assume that the spectrum that we saw is composed of two components. One of those components is methoxyacetylfentanyl, and one of those components, and this is the thing that's a little bit confusing. Let me go back to the very beginning when I had all four of these things. And one of these components is something else, and it's not really clear what. But this is, again, one of those places where, just to go back to something else Ed talked about, the retention indexes can help us a little bit. They don't help us as much as we'd like, but we look at the retention index and we find that the cyclopropylfentanyl has 2914, the crotonal fentanyl has 2914, which is in and of itself surprising, and the methoxyacetylfentanyl has 2914, and this other fentanyl up here is at 2854. Now, assuming that the retention indices that we've got are even remotely good, then what we've got in that mixture is likely to be something like these. We know it's this one. There's nothing else that was very similar to that has retention index, but we don't know really what whether it's this one or this one. I will tell you, because this was something that was made up, it happens to be this one. So this was a combination of this was an attempt to see how well we could do with a complex file like this. And someone made up a mixture of the cyclopropylfentanyl and the methoxyacetylfentanyl. So let me go back. Right. And just to reemphasize what I had said before, that like in the previous subtraction, the match factor was increased. In this case, it went from 740 to 880, and we don't have the unusual peaks that just those very high mass peaks that were very intense and were not being explained. And we've been able to do this not with AMDIS, which because these things are so close that the algorithms that AMDIS uses don't work very well for this, because AMDIS relies on things being apart. We've just relied on the simple tool of spectral subtraction, and it's a tool that has been in use for a long time. This is sort of something that was back in the days before there was good chromatography. You did spectral subtraction a lot. Chromatography has gotten so good nowadays that you're not as used to doing it, but it's still for things that come out close together, or things that you're not sure are coming out close together. It still is a useful tool, and it's an easy tool to use within the framework of this database. And that's one of the reasons that I wanted to very briefly actually do the demonstration, so that you saw that it was, and not just show you the slide, so that you saw that it was pretty easy. Now, I just have a couple minutes before we're going to break for lunch, and I wanted just to cover a couple of other things that come up within the context of things overlapping, and that's the role of concentration. This is a mixture of O-mustard, which is a chemical warfare agent, and malathion, which, if you're an insect, is a chemical warfare agent. And I start out with a 1-to-1 concentration of the two, and go to 1-to-3 and 1-to-10. And what you see, I'm showing you the 123 ion and the 125. The 125 comes from the malathion. The 123 comes from the O-mustard. And you can see when they're 1-to-1, they're about a scan apart. This is fairly fast. These scans are fairly close. I mean, this is, in some respects, fast chromatography, because you're not getting very many peaks. You're not getting very many scans across a peak. And as the concentration reduces, you get to the point where you really can't tell that this is O-mustard. That is to say, the match factor drops low enough that your identification is not confident. However, AMDIS is still telling you that there are two components there. even though you may have very poor identification, you're at least alerted to the fact that there are two there. And this is sometimes useful, and this is what happens sometimes is coelutions change as the amount of material that you're dealing with changes. And you also can see, and there's not a good example here, but you can see situations where as the concentration of the interferent actually can pull the retention time slightly of the target compound. And just to sort of close on, I've got another situation where I've got a huge background here, and this happens to be octanoic acid, so it has this sort of a typical acid chromatographic shape. This is an extract from paint, and so there's a lot of organic acids in the paint. And I've got a 1/10 of a ppm, a 2/10 and 5/10 of a ppm of mustard. And what you see here is that this is the TIC of the mustard. It really is extremely low, and the at the peak of the mustard identification, only 2.5% of the ion current is associated with the mustard. And so the other 97.5% of it is associated with this. And so they become very hard things to sort out. But AMDIS is capable of doing that. And as you go up, you get more and more of the total ion current associated with your target, and you actually begin to see something in the TIC itself. But what is that? I just want to show you what that looks like. This is this is my lowest scan down here. This is the 1 ppm. But this is the white lines here. The white lines here are the ion concentration for the mustard compound. The black lines are the total ion concentration at this one scan. So you're seeing a very tiny amount of material here, and I'm going to blow this up by a factor of a little more than 10 so that you can see. You're seeing very, very low concentrations of these ions, and yet you're actually capable of identifying these things. And that's really the power of AMDIS, and this is a situation where I actually didn't try this. I didn't seek to see whether or not I could have taken this raw data here and subtracted. I should have done that. I didn't see whether I could have subtracted the octanoic acid and gotten a mustard spectrum in NIST. I kind of think I wouldn't have been able to, but if somebody is really interested, I can go back and do that. Just send me a note. Okay, I'm running out of time. I've actually run over my time, and it's almost lunchtime, so everybody wants to leave. So I just want to leave you with a summary. AMDIS will generally be able to eliminate any real coelution problems that your data will have. But for the cases that it doesn't, the NIST program has a powerful tool to allow subtraction of spectral data and to clean up overlap components that AMDIS can't resolve. Now, all of this assumes that you've got the spectrum in the library. You've got something in the library. You at least have to have one of the two in the library to get anything very useful out of NIST. AMDIS will give you spectra, and it doesn't need a library. But I mean, it does need a library, but the library can have nothing in it. I have a library that I use that has exactly one spectrum, and the spectrum has one peak, and the peak is at a mass of 1. And so it never identifies anything. And that's useful for just getting the components that I can subsequently search. So with that, I'll close, and I've sort of run over, but I'll ask for questions, and then I'll be back later for the more general discussion if there are questions now.
Yeah, thank you, Gary. That was great. I learned a lot, as usual. I definitely enjoy watching you work. Because we're over our limit, as Gary pointed out, maybe we'll save the questions for the panel discussion. I actually have a list of questions too, but I'll save them for the panel discussion. And maybe we'll all head off for lunch and touch base again at 1 p.m. Eastern.